All right, so this is another application of related rates that I wanted to share with you. So first let's read the example and then we'll talk through what's happening. Water runs into a conical tank. You can see in the picture what that means. So a cone-shaped tank with a point down in this case. At a rate of 9 cubic feet per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. So base meaning the top in this case. How fast is the water level rising when the water is 6 feet deep? Now I give you a hint here. It says the volume of a cone is given by this equation. So if we look at the picture here, notice the tank is a fixed size. That's the pink colored shape, peach colored shape. Inside the tank is the water. The water is the green. Now I want you to understand the water is running into the tank. So what is happening to the green section over time? The green section is getting higher and higher and higher. So that means the height of the green, which is your y value here, is getting bigger and bigger and bigger. As it goes up, the radius x is getting bigger and bigger and bigger. So x and y are representing the dimensions of the water within the tank. Okay? We can't actually pinpoint what x and y are because they're changing over time, as the volume of water is changing over time. Now, once you pick a particular moment in time, then you can say what x and y are or find x and y depending on what information you're given. Now, let's look at our volume formula. So we have V equals 1/3 pi times x squared y. We want to know how fast is the water level rising. Okay, how fast? We talked about that one. How fast is just another way of saying the derivative. The derivative, though, of the water level. What's the water level? Can you interpret what that means? Look at the picture. The water level is the y value. That's what you're being asked about. The rate of change of the y value. But if you're talking about fast, you're talking about derivative with respect to who? How fast means the derivative with respect to time. So ultimately, we are looking for dy dt. Okay? Now, to find dy dt, we're going to need to take the derivative of our volume equation. But why this equation? Well, they're giving you information. Water runs into a conical tank at a rate, so this is a derivative because it's a rate, of 9 cubic feet per minute. But this is the rate for who? In this case, it doesn't actually spell it out for you. So you kind of have to look at your units to figure this out. Cubic feet is representing your volume. Minutes is representing your time. So this is the rate of change of the volume with respect to time is 9 cubic feet per minute. So they're giving you the rate of change of volume and they're asking you about the rate of change of the water level or the height of the water. The relationship between the two is this V equation that we have here. What about x though? Did it give us any information about x? So let's keep reading. The tank stands point down and has a height of 10 feet. This height is for the tank, not for the water. And a base radius of 5 feet. This is, again, the tank, not the water. We're interested in what the water is doing. The tank is just what's holding it. So did they give us any information about x? Well, we have one more piece right here. How fast is the water level rising when the water is 6 feet deep? Well, that's the height of the water. That's the y value at a particular time t. At a moment in time. That is one moment in time. You cannot plug that in for your y because we are interested in the rate of change of y over time. If you plug that in for y, you lose your y information. You're stuck in one moment in time and you can't move from there. So what you're going to be doing is you're going to work with this equation. You're given dv dt, so you want the derivative of v. You're asked about dy dt. Like I said before, what about x? How is x going to be dealt with in this problem? We're not given any information about x. We're not asked for information about x. What do we do with x? All right, so here's the geometry trick that you need. You need something called similar triangles. You have the cone for the tank, so the big cone, and inside you have the cone for the water. These triangles that you see here in blue are similar triangles. So the height of the big cone and the radius of the big cone is similar to the height and radius of the water cone. Do you remember anything about similar triangles? Well, they're proportionate to each other. So we have a radius of 5 versus a height of 10 for the tank. This is proportionate to the radius of the water over the height of the water. This is the relationship of x to one of the variables. In this case, it's related to the y variable. Using this information, which is in general, it's not for a fixed moment in time, it's just x and y are changing. The tank is fixed, but you can't change the size of the tank. That's fixed no matter what. So using this information, we can solve for the letter that we don't need. So x, keep the x, multiply both sides by the y, and you end up with x equals 5 over 10. Well, that's just 1/2 y. This information we can use to substitute for x in our volume equation. So this is one of the tricks from geometry that you're going to need in your related rates problems. So our volume equation, like I mentioned before, we do not need the x. We're not asked about the x. We're not given information about the x. So we're going to get rid of it by plugging in what it's equal to. It's equal to 1/2 of the y. Don't forget to square your whole x. So 1/2 y, the whole thing gets squared. And don't forget to bring down your other y. So clean up your work so you're ready to take the derivative. Remember, this square is squaring both of these pieces. So it's 1/3 pi times 1/4. When you square the 1/2, y squared times y. Let's finish cleaning it up. 1/3 and 1/4 we can put together, and we can put the pi on top even if we want. So 3 times 4 is 12. All the y's come together to be y cubed. So what have we achieved so far? We now have a relationship between the volume and the height of the water. If we take the derivative of this equation, we will have a relationship between the two rates of change, the rate of change of volume and the rate of change of the height. So let's go ahead and take the derivative with respect to time, because we're interested in how fast things are happening. Like before, the pi over 12 is a constant multiple. He just chills out. So we end up with the rate of change of volume with respect to time equals pi over 12 times the derivative of y cubed with respect to time. So 3y squared times the derivative of y itself with respect to time. Now, we were asked about dy dt. That's what we're trying to find. We were given information about a particular moment in time. We were told the water is 6 feet deep, and we were told that the rate of change of the volume is 9 cubic feet per minute. So we can plug all that information in. So 9 cubic feet per minute. I guess I can simplify. 3 and 12, so that's 4. So pi over 4. Our y value is the height. We were told that's 6 feet. And then we have dy dt, what we're looking for. Now, if you want, you could solve for dy dt and then plug in. I just find that it's easier to move numbers around rather than letters. So we have here 36 when we square it divided by 4. So 36 divided by 4, that's 9 pi. And then dy dt. We can divide, get dy dt by itself. Divide by 9 pi both sides. The 9's cancel, and we have 1 over pi equals dy dt. Now this is an application problem, so normally we would probably enter this as a decimal. So the decimal value is 0.32 dy dt. To finish off the problem, we would put our units. What are the units for y? The height, those feet. What are the units for time? I don't remember, so I'm going to go back up and look. So units for time is right here, minutes. So feet and minute, we put those together, and those are the units for our answer. So this is saying that the rate of change of the height with respect to time at this particular moment in time is 0.32 feet per minute. All right? Hopefully that's a good example for you. Again, the similar triangles is something you might see in a homework problem, so you might need to go back and listen to that again. Have fun, practice, study hard, and I'll see you in the next video.